Got it.
Got it.
I was just talking to one of our undergraduates who's doing a senior thesis in silicon nitride, and I tell him, boy, you want to be there at 3:30.
What kind of work is he looking at?
He'll tell you all about it.
Well, it's such an interesting material. Did you know they use silicon nitride in electronic memory too? And actually, that's how I found out. That's how I learned. We were trying to lower our losses, and I had suspected that there was surface damage going on during the processing when we were forming dangling uncompensated bonds at the surface of the nitride. I mean, I just knew that there was some kind of absorption going on with uncompensated bonds, but no one had ever looked into it. So I was like doing these searches, and all of a sudden I ended up with this paper about people making memory in silicon nitride for RAMs by purposely damaging the surface and writing data into it. I was like, oh, there we go, bingo. Wow. And so they were doing SIMs, and so we just followed that trail. It was pretty awesome. You never know where stuff is going to be hiding under a rock.
Yeah, you got to keep your eyes open to all those amazing things that pop up.
Mm-hmm. Yeah, I don't know if we'll ever get fiber-like losses on chip, but it is kind of my goal is to like get there.
Well, because you can't make the chip very long anyway, so who cares?
You would think. The question is, how do you measure it too? I think we'll be able to get up to 5 billion Q someday.
Wow.
On chip. Which would correspond to below 0.01 dB per meter.
Yeah, like I said, you have to leave it on for a year in order to measure it because the line width is so narrow.
Yeah.
Right, Govind, we used to joke about this with lasers, that the laser line width is ultimately limited by, you know, how long you turn it on for and then turn it off again. And he's actually almost at that point right now. It's incredible. Yeah.
Yeah, at Jun Yi's group at Jilla, he's got his laser stability, I think, to about a couple of seconds over the age of the universe. It's amazing.
I guess at that point in the Spaceballs movie, they call it ludicrous, right? That's ludicrous speed.
He's in ludicrous mode, no question. I mean, and the fact that you can measure the gravitational time shift across a millimeter distance, I mean, it's mind-boggling.
It's crazy.
Yeah, I see that nobody's picking coffee anymore in the auditorium there. That everybody has sat down and having their coffee. So maybe this is the time to introduce them. So Xicheng and Wayne, both of you are going to do the honor. So I pass it over to you.
Yeah, Xicheng, I think we'll go in historical order here because so I knew Dan when we were both undergraduates at the University of Rochester. And he was in electrical engineering. I was an optics undergraduate. So we crossed paths when he was working in the research group of Gerard Moreau, as you all know, the one who went with Donna and eventually won the Nobel Prize. So Dan's first publication, did it say it had published more than 500 papers or something? Dan, your first paper was published right here in Rochester. Don't ever forget that. Picosecond microwave pulse generation by Moreau, Blumenthal, Conger, Gable, yeah, and Stan Campiano, published in 1980. So right as he was an undergraduate. Dan, I just wanted to tell you, you have 0 citations on that paper. I'm sorry to tell you. I don't know why, but anyway.
Was that the post-deadline one?
It might be why, because it was, yeah, I think it was a conference proceedings. So, but anyway, not to feel bad. It was your first of 500 something papers, but everybody knows you have to get started somewhere. So then he got his undergraduate degree and then he went on to Columbia. So Xicheng will pick it up there.
Right. Actually, in 1987, that's probably sometime we have students who are not born yet. So when I was at Columbia University and I was assigned office in called Center for Telecommunications Research. So my office and the Dan's office just door to door. And we have about 2 or 3 people per office. Then during that time, I know Dan. And actually, I also realized that Dan's very earlier work is the second paper, maybe the first journal paper from optics letters. That is microwave photonics using a laser, using a picosecond laser.
Yeah, it was the first
Really
terahertz
microwave.
work.
Yeah, that's
Yeah.
first one. They didn't call terahertz, probably they call microwave, a picosecond microwave.
Right.
Other one actually got over 100 citations.
Yeah.
And that paper was also actually done. That was a paper I cited in my first paper with Dave Austin.
Really?
Yeah, and actually you probably know Bell Lab and Rochester during that time are not probably best friend during that time because due to some political issue, people discuss who is first. Then when I said your paper, actually it's Gerard's paper here now, and not everyone support the way which I wrote it. But I went to Dave Austin. I said, look, this is a paper with Gerard, and you are the corresponding author, or maybe the last author. And actually, Dave is really supported here now. So we said your paper. Now I think it's really good. Dave and Gerard actually talk, and they are really can support each other now.
Mhm.
But anyway, so I have a privilege here to also invite Dan Blumenthal to here, through the Zoom here now. And unfortunately, due to the mechanical issue here, Dan couldn't make it. And Dan actually is a distinguished professor in used to be called Party School, University of Santa Barbara. It used to be called Party School. Dan, you probably remember or not. But now it's become one of the major research universities in US here and have many outstanding faculty. They also call Bill West. So when Dave Austin has his 70 years birthday, Eric Yip and a number of people, we went there together to celebrate. And we really absorbed the major change here, which is different than the 30, 40 years ago we visit. But rather than cutting the introduction short here now, and I'm really pleased Dan will share his recent and also his view about this integrated photonics project here now. Dan, back to you.
Thank you, Zisheng. And Wayne and Zisheng, my DNA is based on my time with you guys and in Rochester and at Columbia. And, you know, those days, they set me forth. So Wayne, you're right. I mean, those days of up in the near Dave's couch that he slept on all the time. Is that couch still there? And at the laboratory for laser energetics, those were just the best days. They were just amazing. So there's a lot of inspiration here from the days at Rochester and Columbia, and when I get into presentation mode. So I'm going to talk today about, it's really an evolution of the work. I've been a faculty for about 30 years now, and the work has evolved over time. Where we're at today is this unified, I see it as a unified world where integrated photonics brings together the atom world and the communication world. So I'll talk about silicon nitride integration, about in particular stabilized lasers and photonics, and how you can use them from the visible to the infrared for quantum communication, quantum and communications. Today, a lot of work done in precision sciences is dominated by AMO, atomic and molecular optical physics. About 90% of these experiments are lasers, optics, and controls. So ions for quantum computing, gravitational wave detection, LIGO, atomic clocks, and entangled atoms for quantum sensing. You can see these are all the good old tables of lots of lasers and optics as we used to like to do in the good old days. They still exist today. And but the forefront is quite different. I mean, as you can see here, there's something called a stabilized laser. These lasers have frequencies that are so pure and phase noise that is so low that the light is as if it was turned on at the beginning of the universe. So Junyi's group, they take arrays of atoms, they trap them, and then they quantum entangle them. And in that way, they can listen to their heartbeats through quantum entanglement are all locked together. They're coherently locked. They trap them in a lattice, and the fractional frequency noise of these lasers is 10 to the minus 21. Which is quite amazing. And now they can listen to the timing of these beats across a millimeter spacing and detect the shift in time due to gravity. The technologies used for these lasers are tabletop. The lasers are stabilized so that they can talk to the atom using reference cavities. In this work here, you have a silicon machined cavity out of single crystal silicon with a vacuum between the mirrors. The mirrors themselves are silicon. Then it's cooled down cryogenically in an acoustic environment. This is one of the best cavities that you can get. Other cavities, which are the previous generation, but still widely used, are shown here at the bottom, a vacuum glass spacer with semiconductor mirrors attached to the end of these cavities. And I'll talk a little bit about what these cavities are and what they do. But if you could take these systems and put them on chip, and my chip picture is missing, what could you do with them? You could do new physics and discoveries, position, navigation, and timing, quantum computing, communications and sensing, test and measurement, space-based and mobile applications, and even coherent WDM fiber data center interconnects. So the technology that I'm going to talk about, moving these technologies to the chip, and will enable whole new classes of applications. Here are just some examples of an atomic clock and quantum sensor on a chip, or laser optical gyroscope, or multi-terabit per second coherent transmission and receiving, or photonic microwave synthesizer. And all of these chips are shown with silicon nitride waveguides. And by the way, this picture was drawn back in 2018 for our Nature Photonics paper. But as of today, we now build all of these on chip. So all of these are now being made today, state-of-the-art systems, even photonic microwave synthesizers. And I'll show you some of the results. What I'd like to do is digress for a minute. Laser line width. When we read books, undergraduate books in optics or physics, we learn about line width and how to talk about full width, half max line width. But it's only a typical value that we talk about, but it's not the full picture. Interpretation of the line width really depends on the application, the observation interval or the experimental interval. For example, an atomic clock, you have to prepare the atoms, reload them, and you have dead times over which the laser needs to be stable and within lock range of the atom transition. That's how you would define the line width of the laser for an atom clock. An optical gyroscope needs to be stable between recalibration times and the degree of accuracy while it's self-guiding. How far would it take to walk off? These are what define the line width. Quantum state can't be disturbed by laser noise in certain frequency bands. So all of a sudden line width may not even be used. It may be actually more like what we would use for microwave systems where we give a noise as a function of offset frequency. So for these systems, what we need to do is really drill down into the frequency and phase noise and drift information. So it would be helpful to start talking about the sources of noise for a line width. And so the front end of this talk is a short tutorial, but I think it's important to bring all of this together. At the most basic, a laser is quantum noise driven. So spontaneous emission, you put a particle into an excited state. Vacuum fluctuations are what cause that particle to go down and emit, or another a photon will cause stimulated emission. But in spontaneous emission, it's quantum noise. And so if we look over here, we see a complex plane. We see a vector that shows the strength of the field and the phase of the photon. And as photons are emitted in a cavity due to only spontaneous emission, the photon phase will wander around like random walk. Its amplitude will be bounded by a restoring force given by the interaction between photons and the excited carrier states. But the phase is not, there's not yet a restoring force to the phase. So it will wander over time over, say, a 2 pi radius of phase. And by the way, that's an important metric that we'll use a little later. Of course, there's collectively, it's not just one photon, it's a collection of photons, but it's just easier to talk about one photon schematically. This process is memoryless, it's Markov, and this is represented by white frequency noise. If we look at the frequency offset from carrier, we represent this process, Markov, as white. This memoryless process goes hand in hand with a Lorentzian line shape. So Markov, memoryless, white frequency noise, Lorentzian line shape, they're all the same thing. They're just different ways of looking at the same thing. The work that was done in the early days by Shallow and Towns, originally with the maser, which was below threshold, and then modified to account for above threshold, leads to something called the Shallow Towns modified fundamental line width. And the reason it's called fundamental is because it's quantum noise driven. Bottom line here is that the fundamental line width is driven by two factors. One is the ring down of the cavity, and the second is the average number of photons in the resonator. And this is a perfect laser, it's a perfect two-level system laser. That's the best that we can do, unless we figure out some tricks about quantum noise. But given quantum noise is the fundamental, this is the best we can do in a laser that has a cavity with some Q factor and some number of photons given by the mode volume of the cavity. When you go to a semiconductor laser, you have to adjust this line width because there's broadening of the line due to the interaction between the intensity or the field itself and the index of refraction of the cavity. And you adjust the line width with well-known Henry factor shown here, alpha squared. So the line width grows from its modified Shallow Towns limit according to the Henry factor. And then there's, of course, also the quantum noise from the coupling between the spontaneous into the stimulated emission itself, NS, which is pretty close to as good as you can do in a semiconductor laser. So we'll get back to this in a minute. But I'm also going to talk about Brilliant lasers, and Brilliant lasers also have a line width that builds upon the Shallow Towns. There is a line with narrowing factor, which I'll talk about, kappa squared. There's also thermal quanta as opposed to optical quanta in the semiconductor laser. We get both here, but in a Brilliant laser, thermal quanta dominates the line width. And then recently, Kerry Valhalla's group at Caltech did great work to show that there is also an alpha enhancement factor for Brilliant also. So you can see that these equations are very related to each other, and they all tell you what the Lorentzian line shape is going to look like. But that's only part of the story. Inside a laser cavity, there is material. And whether the material is in the laser cavity itself or in a reference cavity, which we saw early on in the talk, there is now memory in the system. So there are atoms or molecules inside the cavity. There are atoms or molecules on the mirrors themselves. And we see that there are all these memory type noise effects. There's acoustic and environmental disturbances. Oops, there's ambient temperature changes. Thermal itself has quantum noise that drives something called thermorefractive noise. We also get photons being absorbed that will temporarily change the temperature of the local environment that the next photon sees, and that's photothermal noise. We get photoelastic noise through the electrostatic effect. And the mirrors themselves will also see vibrations. So there's all these noise sources that are dependent upon the volume and the temperature, and they're typically modeled as polynomial noise, 1 over f to the n. You can see here, you can build up a composite noise with 1 over f to the n, but I'll very quickly just talk about flicker noise, 1 over f noise itself. So when we get into the laser itself and into the reference cavity, we have to look at these sources as well as long-term ambient changes, which lead to drift. So if we were to put all of this together, we start to see a development of the laser line shape. And so this is an illustrative example. There's a camera there to take a picture of the spectral content of the laser output. And if we were to have a very fast camera shutter, we would see the fundamental line width of the laser, the memoryless line width, which is shown here. And you can see the frequency noise that we saw before. There's another picture down here, which is called an Allen deviation. And I'll talk about that later. But what it is another way of looking at the picture by capturing the spectrum of the laser, the noise spectrum, and then comparing it to itself sometime later. When you do that comparison on very fast time scales, you're going to see the Lorentzian line shape. And that comparison, that integral overlap, is going to look like this line right here in fractional frequency stability. So basically what we're measuring is how fast is the phase noise moving around as a function of this averaging time. And for the Lorentzian, that's this left side of the ADEV. Now, what's interesting is once we start building memory into the system, through the effects that you saw on the other slide, with the 1/f noise, it starts building up the shoulders on this integral line, on this fundamental line width. And when we start averaging our snapshots, say over 1 to 100 microseconds, we're going to start integrating the line width, and it will look more Gaussian. So in other words, the 1/f noise builds Gaussian shoulders onto our Lorentzian, and the tails are pretty much Lorentzian defined. And so we have a composite between this white frequency noise and this 1/f noise. And that starts coming about in the ADEV from this next part of the curve right here. And this is integral line width. This Gaussian line shape itself becomes like a discus, center of mass, and it will start actually jumping around or jittering in time due to other effects. We call this fractional frequency noise. So the question is, if you have this integral line width, which looks like a Gaussian, and it's now jumping around, its carrier frequency is jumping around, you've now taken your camera shutter and you've slowed it down enough to see this jumping around. This is the bottom of the Allen deviation, and this is a very important point. You'll see this in all applications. For example, in quantum and atomic clocks, people will quote this bottom of the ADEV curve because that's the open loop time over which your laser will stay within the lock range of the atom transition. In optical gyroscopes, you'll see the bottom of the ADEV curve be quoted as the stability of the gyro, because that's how long it needs to take between calibration times when you have to recalibrate to GPS or something else. And now once this jitter line shape moves around, if you were to look at it and integrate it, well, your line width now looks like that whole period just filled in, right? So, line width depends on the observation time. And if you were to even go a longer time period, like a second or more, that whole jittered line width shape will start drifting away. And that's shown by this upper part of the ADEV. So it's like having a boat tethered to the dock. The boat itself may be drifting around at high frequencies and small frequencies. So the mass of the boat, which is the integral line width, is moving around, but it's tethered, and then you let go and the whole boat drifts away. Maybe later on it comes back. So this is how we look at line width. We look at the noise properties, and we look at the ADEV. And so, the question is, how does one define line width? There's two common definitions that people use. We use these. One is you integrate the frequency noise, and by the way, this is offset from carrier. You integrate from infinity in until you get to 1/pi area. And that's equivalent to the Brownian motion of a random walk around 2pi. This measurement here is a single sideband measurement. The 2pi is a double sideband, so that's why it's pi instead of 2pi. And that will lead to something we call, when that integral is 1/pi, we drop down to the frequency, and we call that the effective line width for 1/pi integral. Another way of doing the line width is to take into account the shoulders of the Gaussian. And when you do that, when you take into account the 1/f noise, famous paper by Domenico comes up with this separation line, and you integrate the area underneath this line, and that's the area of the Gaussian line shape itself. And as you can see, there's a transition between these two types of line shapes. But in the end, the line width really depends on what you're trying to do. I mean, if we were running a system that was 10 seconds between capture times, the line width might be just dominated by drift. And you could say that that is a drift dominated line width. So the question is, what happens when we try to take these technologies and move them to the chip scale? What do we need to do? And then we'll come back to line width and frequency noise later on. We need an integration platform that can be very low loss. We happen to be interested in applications that go from the visible all the way to the IR. We want to have something that's very foundry scalable, something that can be in a CMOS foundry compatible. We want to be able to tune and modulate and control circuits on this platform. And we want to integrate a wide variety of components, passives and also actives. So couplers, splitters, delay lines, mirrors, cavities, and then phase shifters, control modulators, switches, and gain blocks, and so forth and so on. So the platform that I'm going to talk about today is the silicon nitride ultra low loss platform. There's an article in the proceedings of the IEEE if you want to read a little more about the history. The structure is shown here. Typically, we start with a silicon semiconductor substrate, a silicon substrate, about 1 millimeter thick. We thermalize the silicon by putting it in a high temperature oven. Since the silicon is so flat, the thermal oxide takes on the same flatness properties. Today, we actually can grow it, or we deposit ourselves, but that's relatively new work. And then we deposit silicon nitride on top of that thermal oxide. We pattern and etch the waveguides, and then we deposit an upper layer of silicon dioxide on top. And there's just a lot that goes into this process. But today, the state of the art that we have in our lab, which is the world records, we have 0.034 dB per meter. That's the loss that we have on chip. We are able to build resonators with cavity Qs that are 720 million on chip. That's in the IR near the telecom band. In the visible range, we're able today, and this is a recent result, to do 0.5 dB per meter at 780 nanometers. And our current resonators at 780 nanometers are 160 million Q. Moving from about 461 to 802 nanometers, we have ranges of 0.01 dB per centimeter to 0.909 dB per centimeter, and cavity Qs that are 60 million to 9.5 million. But our recent result at 780 nanometers means that we're probably going to have all of these numbers are going to bump up. We also have in this platform, we'll talk about, we have stress optic modulators, which allow us to run from DC to 20 megahertz. These modulators have a very important characteristic, is that they don't affect the optical loss of the waveguide. So we can maintain the loss characteristics and put modulation on top. These are fully planar with the CMOS foundry. I'll show you that. And of course, the full range of passive and hybrid components. So one of our recent results, 422 million Q cavity with a 900 kilohertz line width, was the first time that we hit under a megahertz. But I just wanted to talk about this picture really quick about what we had to do to get the losses down. We had to take care of bend radius losses. In other words, you don't want the mode to get disrupted by the bends of the waveguides. There are many ways to look at that. So many of our devices will avoid something called critical bend loss by having a minimum bend radius. We also have scattering inside the material. We have absorption inside the material, both the oxide and the nitrides. And then we also have the scattering turning into radiation modes, absorption turning into heat. We get point defects that we have to deal with. And then we get surface effects. Like when we do the etching, we get uncompensated bonds. that can form silicon OH, silicon H, NH, and just silicon. So there's all kinds of loss mechanisms that we deal with in our processing. And when we work really hard at it, we can then get down to 0.034 dB per meter and 724 million Q. And what's amazing about this particular work here is that this was done on a 200 millimeter CMOS foundry compatible wafer, which is shown here on the lower left. You can see that here we're hitting a 386 kilohertz line width for these resonators, and you can see the Q and the ring down time for this work. We're also able to do this at visible wavelengths, and you can just see our resonators here operating at different wavelengths. Now, why did we choose these wavelengths? Well, 698 is the line for neutral strontium atoms. 674 is the clock transition for an ion strontium. 802 and 461 are both cooling lines to cool the strontium neutral atoms down so that you can then turn them into a clock or some other function that you're going to do with them. Today, this is the latest results. So these were just presented at IPC in Vancouver just in November. We have record low losses at 674 and 780, so 0.65 per dB per meter and 0.5 dB per meter with intrinsic Qs of 103 and 90 million. So we're really excited about the performance of the visible light chips because I'll show you applications here also. Next, we want to put modulation into this platform. Silicon nitride doesn't have an electro-optic effect, so one will put lithium niobate or other materials on the nitride platform to get that effect. You can do thermal also. There has been work with aluminum nitride and under-etched PZT, stress optic modulation, so a wide range of modulation. We wanted to give the platform a fully planar, so no under-etching. We wanted to have high performance. We wanted to be able to hit tens of megahertz of modulation, high extinction ratio. We also wanted to be able to tune a DC. So aluminum nitride is not a good DC tuning. Aluminum nitride also needs resonant modulation. It works well at one frequency, and we wanted broadband. And we also wanted to maintain our low loss. So this is work, Jiaowei Wang, the group, in collaboration with Army Research Laboratories, Ryan Rudy. You can see here a chip with a series of ring modulators on them. Basically, this is the structure I showed you before, right? The low loss with the silicon, the lower clad, the upper clad, and the nitride waveguide there. The PCT is deposited offset from the optical mode so that there's no interaction between the material of the PCT and the optical mode. So we don't affect the Q of these cavities at all. And what we do is we now form a strain and a stress between these two electrodes, which changes the index of refraction of the silicon nitride waveguide very strongly, actually. So we can maintain the Q of these waveguides. For example, in this particular run, we had a 7 million Q with a 54 megahertz line width. And then we are able to tune this resonator across a pretty wide range. But the nice thing you're going to notice here is, do you see how this is the all-pass function of these resonators? So all frequencies except for the resonant frequency, we get really good extinction ratio. But as we apply the voltage and tune it, notice that the Q of the cavity is not changing. This is a very different behavior than you'll see in silicon nitride and silicon resonators. If you see a silicon resonator, you're going to see this line shape fatten up, and you'll see its peak decrease because there's loss being introduced into the cavity. And so you can see here that we get a really good behavior of these modulators. The other nice thing about these modulators, by the way, is that they work with any of our waveguides from 400 nanometers out to 1700 nanometers. So you don't really care about the wavelength of operation, which is a huge benefit. We get good modulation bandwidth, DC out to about 15 megahertz today. There are three components of the modulation bandwidth: resonator, photon lifetime, electrical RC time constant of the electrodes, and the PZT optomechanical bandwidth. And today we are PZT limited, but we get out high enough to do what we call a control function. So there is putting modulation of data or information onto a carrier, but then there's also controlling the laser. And I'll talk about this in a minute. Locking the laser to a cavity, locking it to a resonator, trying to keep its output power constant. And all of those control functions fall within this important range of tens of megahertz of modulation. We also look at the linearity of this modulator too. We get good linear performance. We measure, this is shown here. So with this modulator, we showed two demonstrations in the Optics Express paper. The first one is using it in place of an electro-optic modulator for laser frequency stabilization. So what you see here is a laser that is referenced to an on-chip cavity here. So basically, we're going to lock this laser to the quadrature point of the reference cavity. We're going to lock it right there. We're going to do that by dithering the laser and creating two sidebands with our PZT modulator. So the PZT modulator is replacing what was traditionally done with an EOM. In this experiment, we still use an acousto-optic modulation device to frequency shift the laser and align it. And the double sideband modulation is used with this feedback loop, PID loop, and it's going to take the AOM and lock it to the ultra high frequency cavity here, this chip right here. And when you do that, the signal coming out of the AOM, essentially the laser light, now takes on the characteristic of this cavity here instead of that of the laser. And if this cavity is well behaved, if it has low noise, you will reduce the integral line width of the laser. And as you can see here, here's our frequency noise plot. Here, blue is just the laser running by itself. Now we turn on the reference lock to this cavity, and you can see the frequency noise is improved by over 4 orders of magnitude improvement. So this is what you're going to see in this talk over and over again. We're able to drill down the frequency noise by significant proportions over its free running state. And the dotted line here, by the way, is something called the thermorefractive noise floor of this particular cavity. It's related to the volume of the cavity and how much thermal quantum noise for that cavity will be the limit. And so you'll see in our plots that we pretty much always have this dotted line here for the particular cavity. And what we're trying to do is take this noise and drill it down as close to that line as possible and make it thermorefractive noise limited. Okay, this particular plot goes down to about 100 hertz. There's issues down here that I'll talk about later with measuring this very low frequency noise. The second application that we did with this modulator is something called laser frequency tracking. So if the laser itself is moving around, the carrier is moving around, we can take our modulator, wrap a photodiode, loop around it like this to keep the output power constant. And now this modulator tracks the laser, and we're able to track the laser up to a megahertz, limited by the bandwidth of this closed loop feedback. That's useful in WDM add drop, WDM transmitter rings, and laser stabilization. So these two very important functions can now be done with this on-chip silicon nitride modulator technology. So how do we start putting some of this together? So first of all, we have our fundamental noise that we talked about, right? That's the quantum noise of the laser itself that gives us this far from carrier or the wings themselves. Depending on what laser we use, we can have better performance. I'll talk about a Brilliant laser, which has a nicer high frequency content itself. We make Brilliant lasers, by the way, at infrared and visible wavelengths, and I'll talk about that. So that's our high frequency noise. Then we're going to take our laser and we're going to lock it to a reference cavity, like we looked at the beginning of the talk, and we started seeing some locking going on, but we'll talk about it in more detail. When we lock the laser to the reference cavity, we take its close to carrier noise and we bring it down to that of the reference cavity itself. So by employing these two techniques, the final laser line width or frequency noise is now dictated by the resulting curve. We tend to use something called pound-driver Hall locking, which is developed for the laser gravitational wave detector, Jan Hall and colleagues. We use different kinds of devices. This was some of our early work with a NIST micro rod, about 2.5 centimeters. And basically, it's a very small version of those big cavities that I showed you before. Very good performance. They still are bulk optic. So the question that we want to ask is, how do you start putting all this on chip? A new era of integrated laser stabilization. So we can imagine having, for example, a gain block attached to a tunable laser. So now you're seeing all of our silicon nitride photonics on a chip, right? We have waveguides, we have ring resonators, we have PZD tuners, we make things like splitters and reflectors, couplers. We're going to make spirals and coils and have modulators. And we're going to put them together on a chip to realize a stabilized laser. So we have a laser, we can tune it, we can get nice low fundamental line width, we can bring it in and we can lock it to a reference cavity. We can take the output, we can modulate sidebands on it. So now we can do things like talk to an atom or quantum or position navigation or coherent communications. So this is the vision here. The other part of the vision is, how do you cascade different cavities together? Remember before we talked about the far from carrier and the close to carrier. Another way to look at it is, I have some kind of a laser that's working on a nonlinear hot cavity to drill its far from carrier noise down as low as possible. And then I use my cold cavity to lock that to now stabilize the laser. So another way to look at these applications is, you have a hot cavity and a cold cavity. A hot cavity and a cold cavity. And the hot cavity is running nonlinear to reduce the high frequency content, and the cold cavity is going to be used to reduce the low frequency content and stabilize the drift. So very early on, our work started with Brilliant lasing. To quiet down the far from carrier noise. We actually have, as you've seen, these resonators here. So light comes in, goes into the resonator, and light comes out. But we actually use this resonator to make a nonlinear device called a Brilliant laser. And early on, we were able to achieve sub-hertz. So this was the first sub-hertz laser on a chip that was demonstrated with Brilliant lasing. It's good to look at what Brilliant is. It's a nice nonlinearity. It's 2 to 3 orders of magnitude larger than the Kerr effect. What happens is light goes in. We put light into a waveguide or a material, in this case, a waveguide. And the light randomly scatters, so you can not well see. Red light is scattering back. There are small frequency shifts due to the collisions. But any light that's scattered back in the same direction will start forming a grating. As you turn the light up, even though a lot of light is scattering in random directions, the light that is scattered back forming the grating starts reinforcing pump photons to scatter more light back. And so as the grating is formed and then it reinforces itself, we move from the spontaneous, the prior spontaneous, into what we call stimulated, where there's reinforcement. And now the pump waves are now very efficiently scattered from the grating. The other thing to notice, though, is that the light being scattered back is slightly offset. This grating itself is being formed by a stress optic effect in the material itself. So literally the intensity of light is compressing the atoms, forming a moving grating, which is a stress optic moving grating. And this becomes our closed loop system here with Brilliant, and we get something called a Brilliant shift because there's that energy difference from the moving grating itself. Red is frequency offset by what we call the Stokes frequency. And this is an energy diagram of pump Stokes frequency and omega. Now, there's something really nice about the Brilliant effect. Because the gratings themselves have a certain bandwidth, shown here in green, they effectively do a filtering of the phase noise from the pump light. So high frequency phase noise is not converted over to the Brillouin-Stokes photons, only the low frequency noises. So we get something called line width narrowing in a Brillouin laser. And the line width narrowing basically goes as the ratio of the acoustic dampening rate and the photon dampening rate. And the bottom line is, if you can make a resonator that has a very rapid acoustic dampening rate and a very long-lived photons, or very low loss, then you can make a very good Brillouin laser, and that's what we've done. So you can see here is our ring resonator in silicon nitride. Pump photons come in, they scatter back, they create these phonons, the green here, but they basically are very short-lived. We reflect back the red light out the output, which is our Stokes shift, and the phase noise is reduced by a factor of 1,000 or more due to this ratio here, this line width reduction here. The other beautiful thing about this system is that since the phonons are continually generated, they're not guided, they're always generated by these very long-lived photons. There is no acoustic guiding going on here. We do not design an acoustic waveguide, which people have to do in other Brillouin lasers. And as you'll see, the beautiful thing about this design is that we can easily translate it all over the wavelength map. We can make visible Brillouin lasers with it, as well as IR lasers. And so you can see here the world's first visible light Brillouin laser made on a chip. This one was at 674 nanometers, literally by taking the laser cavity, designing the free spectral range so that one of its resonances matches the Stokes shift. And then we don't require an acoustic waveguide, so we're able to pump these very efficiently, and we get Stokes light coming out. The line width is reduced, as you can see here. We get line width reduction and coherent collapse of the gratings here. And so we can make these lasers in the visible too. One thing that's really interesting is these lasers like to cascade. They like to have multiple orders of Stokes emissions. So for example, if you pump at one frequency and you have Stokes emission at this resonance here, if there's another available resonance over here, this process will cascade. And maybe that's a good thing, maybe it's a bad thing. We like to see inhibition of the second mode so that we can continue to pump light into the primary Brillouin mode. And this work, the way we did it, is we split the resonance of this second order, which is called the S2 lasing mode. So in other words, we actually designed a photonic crystal cavity. It is a grating modulated resonator where on purpose we split the mode where S2 will happen. And indeed, we can continually drive up S1, continually reduce its fundamental frequency, and there will not be onset of S2 lasing. In this particular example here, we have an 88 millihertz fundamental line width on a chip scale Brillouin laser. And you can see here, we have another type of design that this is a good design here with the grating modulated, but today we make something called a photonic molecule SBS laser. We take one ring resonator and we embed it inside another ring resonator. And here we can now design the energy coupling states like you would a molecule. And we can very precisely split the S2 state so that there's not lasing here. And this also works very well to inhibit lasing. Now you can take two of these lasers together. So you can take the nonlinear Brillouin resonator laser and actually exactly the same resonator and just use it as a linear resonator. And you can couple the two together to do our dual stage line width stabilization. So for example, the Brillouin resonator will reduce the fundamental line width. That's like taking a Gaussian shaped line width and reducing the wings. Then you take your second stage, the cold resonator, and we use it to lock the close to carrier. So that's like taking this Gaussian and narrowing it down to a Lorentzian type using the lock circuit. And then there's a transition that happens over here like this in the line shape itself. In the frequency noise domain, that's like taking our pump laser, reducing the far from carrier noise first, then stabilizing to the second cavity and reducing the close to carrier to give us this composite curve like this. This has been done with bulk optics, just shown here with an SBS laser out on a chip and a micro-rod resonator cavity, reference cavity here. There's some work by William Lowe and colleagues at Optica. But we demonstrate this on chip, and I'll show it to you in a second. I just want to say a quick word about Pound-River Hall laser stabilization. This is in our lab. So typically you'll take a laser and you will stabilize it to this reference cavity. So in the lab, we have this vacuum silica mirror spaced cavity that we attach a laser to and lock it to. This gives us a 1 Hertz laser in the lab, and we use it to qualify our other lasers, but PDH is also used in our laser stabilization. In any of these resonators, as you increase their mode volume, there's this thing we call the thermal refractive noise limit, just shown here in some curves. What you're seeing here is you're seeing a very small resonator, high confinement, very small mode volume. The thermal refractive noise sits up here. Then we start bringing the size of the resonator up. Our refractive TRN floor reduces all the way to here. I'll show you a coil resonator, 4 meters. This one's 3 meters on chip, and you can see that it's TRN. So as we keep increasing the mode volume, we decrease the limit over which this type of system can achieve. And then here's the micro rod, which has a very large mode volume, and you can see it's TRN. So that's really the game that people play, is how to increase your mode volume to get the TRN limit go down. And so here's work that we did with a 4 meter long reference cavity on chip. This is actually 4 meters. Light is coupled from a bus, goes into a spiral, comes back out again. So the next one in, back out again. So this is really just one big ring folded up into 4 meters. And we stabilize our laser to it, and we are able to achieve a 36 Hertz integral line width laser. This is now the actual Gaussian line width that we are able to get, is 36 Hertz on chip. And the ADEV, that bottom of the ADEV floor that we talked about in this case, is close to 1e-13, which represents about 2.3 kilohertz per second drift. Shown here is the frequency noise of the original laser, and then the stabilized laser with the coil is shown here. It actually hits the thermal refractive noise floor. We are able to get our ADEV, which you see here. We've seen these plots before now, and they can show 1.8 e-13, and we measure the drift in the laboratory, which is quite amazing for an on-chip technology. If we can get this performance down to its limit, which we expect, we'll be looking at an 8 Hertz laser that is bordering 5 e-14 ADEV at 10 milliseconds. Today, and this is again another result that just happened, we are able to now make these coils at visible. So we now have the coils running at 674 nanometers. Here you see a 3 meter coil. You need very high extinction ratio, which means you need very low loss. Well behaved. Here's our Qs now, are 40 million for a 3 meter long 674 nanometer cavity on chip. We can take our laser now, our SBS laser running at 674 nanometers, and we can attach it to this coil resonator and actually do what we saw early on in the talk, which is stabilize our lasers and show that we can significantly reduce the line width and stabilize the laser using all on-chip techniques at this point. And this is at 674 nanometers, which is the strontium ion transition. Excellent results. We see 200 Hertz kilohertz line width, 112 kilohertz line width. These are very early results, and they're not near the thermal refractive noise limit today. But you can kind of see everything I talked about early on in the talk, right? How we calculate the 1/pi in line width and the beta line width. We always quote both in our results. It gives us a sense for how the line width is evolving. And today we do this at 780 nanometers also. So here a very recent result of 780 nanometers being run to get order kilohertz line width, and you can see those over here. So here's a 780 nanometer laser, pound-driven hole locked to a reference cavity. I'm going to skip these guys right now to get to the applications. Govind, how much time do I have left?
A few minutes, I guess.
Okay, so we'll get to the applications really quickly then. There's lots of things we can do with these stabilized lasers. One is we can create a very stable transmitter for fiber communications. This is our early work where we take a stabilized laser at the transmitter. You can see the pump, the SBS laser. You can see a rod cavity, PDH lock, transmit to a receiver. One of these stabilized lasers is over at the receiver now, and we take that laser, and since they're so well aligned to each other, we use a very simple loop, about 100 kilohertz, and we snap lock these two together, and we've now done precision frequency stabilization across the fiber. Basically, because the lasers are so quiet, we're able to drill all of the fiber noise out with just a very simple low frequency CMOS phase lock here, okay? Open loop, closed loop. And by doing that, these are quite complicated curves, but I just want to show you that we're able to just narrow the line widths down across the lock. And then once we close the loop, this is essentially the laser that you're running across this fiber length here. This is the phase noise of that laser, which is really remarkable for chip scale technologies. I mean, we are able to drill out almost all the laser noise and basically have a laser, actually 30 hertz laser, running across this link. So now you can think about locking atoms and optically synchronize these fibers. We can get down to about 3.4 times 10 to the minus 7th phase error variance across the link itself. And now I'll show you how we can pipe some data over that and maybe save some energy too. This is just a typical WDM DSP fiber optic link. People go to a lot of trouble to transmit data over a fiber. This is coherent modulation. These are different amplitude and phases. They're called symbols that you're modulating the light, and data is being transmitted over each of these symbol points. So you can go to all these 32, 64, 128, 256, 1024. Think of each of these points here as being turned on off in any time slot. And as you turn off each point, you're modulating that many bits, okay? But in order to recover this data, people build these digital signal processors to capture the frequency and the phase of the light before it can be decoded. These DSPs, they consume 10, 20, 30 watts of power. But what if you could now quiet your lasers down so that you could track the phase and frequency with a simple 100 kilohertz, 200 kilohertz circuit and recover the data without the DSP? And this was our first work. This was our first work of recovering, in this case, 16 QAM data without a DSP by having our Brilliant laser stabilized to one of those micro rods on the transmit and the receive side, and using a very simple 100 kilohertz CMOS loop to recover, to lock phase and frequency. We're now locking two lasers together, getting rid of all the fiber noise. Today, we're able to do this with packaged versions of our Brilliant laser and the coil resonator that we looked at before. And now we're modulating up to 90 gigabaud, 16 QAM of data on top of this, and we recover it with just a very simple phase lock loop. Again, because the laser is so quiet. And by the way, these pinpoints here, That shows how narrow the line width is of the laser itself. And the fact that we can transmit 90 gigabaud 16 QAM over a single wavelength with just simple phase lock loop. We now do it over a whole bank of WDM wavelengths. Today, we transmit 6 terabits of information over this loop without a DSP using combs. And the last thing that I'd like to show you, which I think is one of the most fun things that we do, is today we now take all this down to the visible and we cool and we trap rubidium atoms. Without going into a whole lot of detail, conventionally, what people do is they'll load rubidium atoms into a vacuum cell. They'll use 6 laser beams to cool and trap the atoms in combination with magnetic fields to create something called a magneto-optic trap or a 3D trap. And what we're working towards is taking these lasers, the stabilization cavities, the modulators, all the technologies that you've seen, and putting them on chip and interfacing them to a vacuum cell to actually have a chip scale version of a 3D magneto-optic trap. This is what we've built in the lab today. We have cooling and repump lasers being delivered to a PIC. The PIC takes the light and forms beams, transmits them into the cell, and does the trapping for rubidium atoms. This is what our PIC looks like today. We use gratings to move the light out of the plane, and we have very large area beams, 4 millimeters, 3.5 millimeters in diameter. We want to capture as many rubidium atoms as possible. So literally the light is coming out of the PIC, and you can see it here on the left-hand side, into this vacuum cell, which contains rubidium atoms. When we turn the light on and the magnetic fields, we trap this molasses of 5 million atoms. We cool them down to 200-ish microkelvin. This is first in the world beams produced directly with a photonic chip itself. And we're really excited about these results because from here on out, it's going to enable us to make 2 photon absorption for a clock. We're looking at gravitational detectors with these and an atom clock with this configuration. And there's a lot of people who contribute to this work. My group at UCSB, Yale, Northern Arizona University, Honeywell, NIST, Morton Photonics, Microsoft, and just a great team of people, as well as funding from DARPA, ARPA-E, and others. And I'd like to thank you.
Very good. Very nice. Enjoyed the talk. Sichang, you wanted to go over the questions with that?
Yeah, I think probably maybe we allow the people from the audience directly in Gorgon 101 to ask questions first. Is anyone in the conference room? I couldn't hear anything from the room here now. Okay, I have two questions here. The first question is, it's really impressive to see such a narrow line lasers from this silicon nitride chip. And now I remember actually probably 25 years ago, we talked about silicon carbide. So then if you use a silicon carbide than silicon nitride, what is the disadvantages using silicon carbide?
Zishan, do you remember offhand what the band gap of silicon carbide is?
That's an UV actually.
Okay, so well, one advantage will be that you can go below 405 nanometers. So silicon nitride, our absorption climbs up pretty sharply at about 400 nanometers. Today, to deal with down to about 250 nanometers, we actually make tantalum pentoxide waveguides. I didn't talk about those today, but we make tantalum pentoxide also, not with as good losses, but good losses, and that'll take us down to about, you know, that range. And then if we want to go lower, we use aluminum oxide, aluminum layer deposition deposited alumina will take us down to about 200 nanometers. We have not worked with silicon carbide, and I'm not aware of anybody that's done a lot of work with that material system, to tell you the truth. I suspect it's because of the processing technology of putting down the material and then doing the etching. It's usually what really gets you. You know, it took 14 years to get the nitride to where it is today. We've been working with tantalum pentoxide, and so does NIST, Scott Papp, probably for around 8 years now. And there are issues with etching and contamination. Also, tantalum crystallizes if you heat it up beyond about 500 degrees, so that's no good. So you can't anneal the samples to drive out the hydrogen. Alumina is another layer of complexity because pretty much the only thing that works for low loss is aluminum layer deposition, which takes forever. So as you can see, you know, these material systems are getting harder to put down, to etch, to process. That's okay. I think over time we'll figure them out, but I think that's governed the progression, and probably the same thing will have to happen with what you just asked.
Thank you, Dan. So the second question here is, I can see your laser have extremely narrow line width here for sensing calibration for a lot of metrology application. Such also low loss of your material in this visible to infrared. Is there any advantages you can come up here for ultra fast application, like make short pulse laser rather than very long CW?
Absolutely. As you know, my upbringing is in the ultra fast world. And it was interesting at one point to decide that I was going to part with the ultra fast and pay attention to the universe length existence of light, you know, narrow light. But I think that they come back together again. I think that these techniques can now be merged together with your attosecond pulse techniques. And I would like to see us try carrier envelope stabilization of such precision that we can now interfere attosecond pulses with great precision and explore new field strengths, field engineering, and new techniques, possibly attosecond quantum techniques, if we can do, you know, entangled pulses and such. So I see a carrier envelope engineering using our technology in concert with attosecond pulse technology to go the next step. I think would be great.
Thank you very much, Dan. I have been asked to develop undergraduate laser design courses in the future. So I'm wondering in the future here, I can ask you to do us a favor, send one of your cheap laser to Rochester here so we can show to our undergraduate students for laser design.
I would love to. I'll just send you one to play with in your research too. We do package them now so that you don't have to sit there with $20,000 worth of alignment stages, which is a huge advantage. You can keep the lid off so the students can see them. It's almost more fun to use one of the visible light ones because they just light up. It's absolutely cool. So we could probably send you a visible one and an IR one if you want.
Right, definitely. Thank you very much. Yeah.
Of course.
So Dan, I wanted to ask you a question about the SBS lasers you showed. You said that if you use your laser to pump a micro ring to make a SBS laser, then SBS laser has advantage that it can have a much less phase noise or frequency noise. And one of the reasons you said was because the photon lifetime is much shorter than the damping time of acoustic waves themselves. I think that's what you were saying, that the photon lifetime is much shorter, right?
It's much longer. The photon lifetime is longer compared to the dampening.
Oh, photon lifetime longer, actually. I
might have misspoke.
I see. So photon lifetime typically is of the order of a few nanoseconds, right? Is that correct?
Let's see. Our resonator ring downs. Well, it's the lifetime of the photon inside the resonator.
Yeah.
So our phone, so the lifetime of the photons is somewhere
Oh,
around.
so I see now understand. You're talking about
Yeah.
the ratio of the phonon lifetime to photon
Yeah.
lifetime. You're
Yeah.
saying phonon lifetime is much shorter